Welcome. In this video, I'm going to be talking about material from chapter 2.1 from the textbook Basic Sentential Logic and Informal Fallacies. So the topic here is going to be truth functional operators, and I'm going to start on that by discussing, first of all, functions. Now, a function is something that takes inputs and produces outputs. So you can think of it as a sort of abstract machine, like a bread machine. It will produce as output bread if it's given certain inputs, like flour, yeast, sugar, water, and so on. Most people are familiar with functions, even though they don't realize it, because they're familiar with arithmetic functions. So the big arithmetic functions are addition, subtraction, multiplication, and division. Now, let's look at the function of addition. What it does is it takes inputs and produces outputs. Its inputs consist of two numbers. You input two numbers to the addition function, and it'll produce one number as output. So if you input 4 and 3, it'll output the number 7. Now, a function can be defined in terms of its entire input-output structure. What does that mean, its input-output structure? Well, look at all of the possible inputs you could give the function and what its outputs would be given those inputs. So for instance, if we look at the addition function, it'll have two inputs, and we can just call the first input x and the second input y. Just think of those as a shorter name for first input and second input. Okay, and if the first input is 1 and the second input is 2, it'll output, I'm sorry, the first is 1 and the second is 1, it will output 2. And if the first is 1 and the second is 2, it will output 3. Okay? And so on. Now this table that I have here is part of the input-output structure of the addition function. Now it's only part because there's an infinite number of numbers, so this grid would have to go on to infinity to give us the entire input-output structure. But you can see part of the structure here. Now, what do I mean when I say a function can be defined in terms of its entire input-output structure? Well, here's the addition function again that I just mentioned and part of its input-output structure. Now, suppose I came up to you and I said, hey, I've got this cool new function that I just invented, and I call it richification, and here's the symbol that I'm going to use for that. And you say, hey, that's cool, richification. All right, tell me a little bit about it. I say, okay. Well, if the first input is 1 and the second input is 1, it outputs 2. And you think, okay, that's pretty cool. And I say, well, if the first input is 1 and the second is 2, it outputs 3. And you say, okay, I'm with you. Seems pretty boss. And then I keep going, and it turns out that the sequence of inputs and outputs that I give you is the same as addition. Well, then you're going to say, well, look, Rick, you didn't invent a new function at all. It's the same function. You just renamed it richification, but it's addition. And the reason you would say that is because it's the same input-output structure. There's no more to a function than just this. So if this is the same, then it's the same function. Okay, same input-output structure, same function. Now, obviously, different functions are going to have different input-output structures. So we can do addition like this. We can have subtraction here, and you'll see that for the same inputs, 1 and 1, subtraction yields a different output, right? Addition yields 2, subtraction yields 0. Ditto for multiplication and division. Notice that some functions are order invariant. So for instance, addition will give you the same output, 3, if the two inputs are 1 and 2, but it doesn't matter the order. 1 and 2 gives you 3, 2 and 1 gives you 3. Okay, so it doesn't matter what order they are. Same for multiplication, 1 times 2 and 2 times 1 both give you the same output. So these two functions are order invariant. meaning that if you give them two inputs, it doesn't matter what order those inputs are, it'll give you the same output. Some functions, though, order matters. So subtraction and division, for example, don't give you the same output. If you input 1 and 2, that's not the same as 2 and 1. 1 minus 2 is minus 1, 2 minus 1 is 1. 1 divided by 2 is 0.5, 2 divided by 1 is 2. So the point is just that some functions, order of the inputs matters. Sometimes there are functions where the order does not matter. Now, our topic is actually going to be truth functions. So I only bring up arithmetic functions because people are familiar with them. And so it's a good way to introduce the general idea of a function. But we're not interested in arithmetic functions. We're interested in truth functions. But truth functions are still functions. They still take inputs and they produce outputs. The difference is that the inputs aren't bread and yeast and water, and they're not numbers, but they are truth values. What's a truth value? Well, there's only two truth values, and they are true, which we will label with a capital T, and false, which we will label with a capital F. So those are the two truth values. Now, every atomic statement, just by convention in this class, is going to be either true or false. So if I say something like, I like pizza, that's either true or false. Every atomic statement is going to be true or false. So here's the key thing. The statement operators that form compound statements, okay, so the conjunction, negation, the things we looked at in chapter 1, those symbolize truth functions. And what that means is that the operator doesn't just put together two statements into a bigger statement. Okay, it does that, but it does something else. It determines the truth of the bigger statement as a function of the truth of the components that it put together. Okay, here's an example. So suppose I give you two atomic statements. Okay, I left you my house, I left you my car. These might be things that I would put in my will. I'm giving people stuff when I die. And I symbolize these with H and C. Now suppose then I tell you at some point after class, I give you this conjunction. I say, I left you my house and I left you my car. So it's a conjunction. It's these two atomic statements, H and C, and they've been put together with this conjunction operator, and. And so the statement is actually a big statement, okay, put together with two smaller statements, in this case atomic and a conjunction operator. Now what I said just a minute ago was that not only does it put these two sentences together, but the truth value, whether this whole conjunction is true or false, is going to be a function of whether the two components are true or false. So let's go through all the possibilities. I'm going to make a table here. Here is the compound statement, H and C. Here are the two inputs, the truth value of H, the truth value of C, and here we're going to put the truth value of H and C. Okay, the conjunction H and C. Well, what if both inputs are true? Okay, so I die, they read my will, and it turns out that H is true, I left you my house, and C is true, I left you my house. The question is the conjunction that I told you true in that situation? Well, the answer is yes, of course, right? You wouldn't sort of, go to a sort of medium and try to contact me from beyond the grave and say, hey, you lied to me. No, because I told you that I gave you this conjunction, I left you my house and I left you my car, and that turned out to be true if both of the components are true. So what that means is that, again, I'm just repeating myself, but trying to repeat in different words to make it clear. The truth value of the conjunction, that statement, is going to be true or false. Well, it's determined by true or false, not by how loud I said it, and it's not by whether it started with a vowel or a consonant. What is it that makes that conjunction true or false? Well, it turns out that what makes it true or false is the truth value of the components, the two conjuncts. Okay? Is it random? No, it's a very well-defined function. And part of that is that if both conjuncts are true, the conjunction is true. Well, let's move on. What if the first conjunct is true, but the second one is false? Okay, so they read my will and it turns out that I left you my house. That one was true, but I left my car to somebody else. Okay, well, then was my conjunction a lie? Okay, did I lie to you when I said I left you my house and I left you my car? Well, yeah, you've got a gripe at that point. So what that means is that in English, the conjunction and is false. The compound statement, the conjunction statement is false if the first conjunct is true, but the second conjunct is false. Okay, well, what about if the first one is false, but the second one is true? Okay, I didn't leave you my house, but I did leave you my car. Well, then you still have a gripe. Okay, I still lied to you. Okay, and in the final case, they're both false, right? I did not leave you my house, and I also did not leave you my car. Well, then in that case, I also lied to you. Now, these are all the possibilities there are because each statement is either true or false, each atomic statement. And so we only have 4 possibilities. Okay, they're both true. First true, second false. First false, second true, both false. So there's only 4 possibilities. And we've listed off the outputs for all 4 possibilities. And what we discovered, or what I tried to reveal to you, is that the truth of a conjunction is determined by the conjuncts, and in particular, it's true if both of the conjuncts are true. In all of the other possibilities, it's false. If the first input is true and the second is false, the conjunction's false. If the first is false, the second is true, conjunction is false. If they're both false, the conjunction is false. Okay? So that's an example of a truth function. In this case, the conjunction truth function. What I'm going to do now is go through all 5 of them because we have 5 statement operators, okay, that we talked about in chapter 1. And each one of those statement operators symbolizes a different truth function, okay? So I want to go through all 5 of those. We've already talked about conjunction, so I'm not going to talk about it again, except I'm going to represent it in a certain kind of way. This is the same table. The only difference is that instead of using H and C as letters in the table, I've used these Greek symbols phi and psi. And the reason I'm doing that is because, let's go back up here. By convention with us, H and C stand for atomic statements, okay? And so what this table, strictly speaking, is telling us is that if we have a conjunction where the 2 conjuncts are atomic statements, then if the first atomic statement is true, the second is true, the conjunction is true, okay? But we want conjunction, we don't just want it, it's a fact about English and logic. Conjunction, this truth function holds even if the inputs are themselves compound statements. They could be compound or atomic, either way. And so we want to use statement variables. So in this case, phi and psi are any statement. They might be atomic or they might be compound. And that's why we can't use the Roman letters, is because by convention in our class, Roman letters symbolize only atomic statements. So that's why we're using the Greek letters. It's just to indicate that these could be anything. Phi and psi could be atomic, they could be compound. This function still obtains. Okay, so that's conjunction. Let's move on. Negation is a one-place operator. Okay, all the rest of them are 2-place operators, meaning that they take 2 component statements, atomic or compound, and put them together into a larger statement. So with disjunction, there's 2 disjuncts. With conjunction, there's 2 conjuncts. With a biconditional, there's 2 components. And with a conditional, there's an antecedent and a consequent. So they all take two inputs. Negation is the one statement that only takes one input. Okay, so suppose that we have an atomic statement, I am married. And I can negate that. I can apply the negation operator, I am not married. So in this case, I am married, we'll call that phi, and I am married is phi, I am not married will be not phi. So suppose you're in a chat room with somebody and they give you this sentence, they say, I am not married. Okay, so they tell you this compound, logically compound statement. Okay, well, is it true or false as a function of the statement that it's built up from? Well, suppose phi is true. Suppose I am married is true. Well, in that case, what's the truth value of I am not married? Well, it's obvious, it's false, right? What if, on the other hand, phi is false? The atomic statement, I am married, if that's false, well, then the compound statement, I am not married, is going to be true. That's just so obvious, it's hard to even talk about it on a slide like this. But basically, negation is just the opposite, right? If you input true, it outputs false. If you input false, it outputs true. So it's actually a very simple function. It just gives you the opposite truth value. Easy to memorize. Let's move on to disjunction. So here's two atomic statements. Shelley won lotto, Shelley got a big inheritance. And I can put these together into a disjunction. Either Shelley won lotto or Shelley got a big inheritance. Okay, or I could state this another way. Shelley either won lotto or got a big inheritance. Doesn't matter. So suppose we're walking down the street and we see Shelley drive by in a brand new Mercedes convertible. Okay, and we know Shelley, she is a student who doesn't make a whole lot of money, but she's in this brand new car. And so I give you a guess as to why she's driving this big car. Okay, I say Shelley either won lotto or got a big inheritance. So we've got two disjuncts here. Shelley won lotto, Shelley got a big inheritance, and I put them together with a disjunction. Okay, and I gave you this guess. Now we want to determine the truth function of this. Well, what if both are true, right? We stop Shelley, we wave her down, she pulls over, and we say, hey, how could you afford this car? And she says, oh, it's amazing. I had this amazing week. I won lotto, and then I got this big inheritance. Then was my guess right? Well, yeah. Okay, you might say it's doubly right, but you wouldn't say, oh, Rick, you were wrong, right? You guessed that, she won lotto or got a big inheritance, but, she got both, right? Well, no. My guess was doubly correct. If you have a little bit of an intuition to the effect that maybe that should be false, hold on, I'm going to talk about that in a minute. But for now, hopefully most people agree that it would be a bit weird to turn around and say that my guess was wrong as to why she could afford the car if she just had a really, really lucky week. Well, what if after we flag her over, the first disjunct is true, but the second is false? She says, oh, I won lotto. And we say, well, did you get a big inheritance? And she says, no, I didn't. Okay, so the first disjunct is true, second is false. Well, my guess is still right, okay? Because my guess was, well, she either won lotto or got a big inheritance. And if she won lotto, then clearly my guess was true. What if the first disjunct is false and the second one is true? Well, still, my guess was correct. I was on. She says, well, no, I didn't win lotto, but I did get a big inheritance. You turn around to me and say, ah, you got it. You nailed it. I say, yeah, I had a feeling. The only situation in which you would turn around to me and say, ah, your guess was wrong, is if they were both false, right? We wave Shelley down. She pulls over and, hey, how'd you get the car? She says, oh, I robbed a bank yesterday and I bought this. You'd say, oh, well, Rick, you were wrong. Sorry. And yeah, I would have to agree you were right. So if both disjuncts are false, then the disjunction is false. But in all other cases, it outputs true. So the disjunction operator outputs true when both inputs are true. First is true, second is false. First is false, second is true. And if they're both false, it outputs false. Okay? Now, in English, the word or is really ambiguous. Okay. Logically, there's two different truth functions that English uses the same word for. And typically, that's not a problem because we know from context which one someone means. So we usually don't even realize there's two different functions because we're so good at knowing which one someone means. That's so automatic that we don't even realize we made a choice. But in English, sometimes it can mean this. And an example would be, you can have soup or salad, right? The atomic statements here would be something like, you can have soup or you can have salad. This might be at a restaurant. This might be their policy. Well, in this case, they clearly mean to be ruling out a situation where you say you want both. If I say, well, okay, that sounds good. I'll have soup and I'll have the salad. They'll say, no, 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 no. You can have soup or salad, meaning you can have one but not the other. Okay, well, in that case, the truth function would return false when both inputs are true. Everything else is still the same, right? If I said, oh, wait, are you telling me that it's false that I can have soup and it's also false that I can have salad? They would say, no, that's wrong. That's not what I meant. They would specify that what they mean is one of these two situations. They're ruling that out, and they're also ruling that out. That's a different truth function, right? Because it's got a different input-output structure from disjunction. In particular, it differs right here in the situation where both inputs are true. Now, that can sound bad, but really it's not that bad. What it means is that we just have to realize that there's really two different functions here. The one we've been dealing with, and we're going to continue to deal with, we will call inclusive OR. We can call inclusive OR, and that's just the one I talked about first. It outputs true when both inputs are true. The other one we could call exclusive OR because it excludes the possibility that both inputs are true. If we had to come up with a symbol, we might use this one. The point is, don't worry about this. From here on out in this particular class, we're only going to worry about this function. Anytime the word OR shows up, we're just going to assume it's inclusive OR. We're going to use this symbol. We're not going to worry about this symbol or this truth function at all, okay, just for simplicity. Now, don't worry, because if you wanted to express that function, we could still do it. We could say soup or salad and not both. And this will make more sense later on, but we're not losing any power with our formalism by not including this operator. Even though English uses it and uses the same word or, we're not going to, and it's not going to be a problem for us. So we can just ignore that from here on out. Okay, next up, conditional. This one's going to be tricky. So here's two atomic statements. You turn in all the homework. And the next one is, I give you an A in the class. By the way, this is not official grading policy. As of the time I am recording these videos, there's no homework actually in the class, but suppose it's a different class with a different grading policy. And suppose that you come down and you want to know how you can get an A or something like that. You want to know about the policy. And I give you this conditional. I say, if you turn in all the homework, I'll give you an A in the class. So I tell you that conditional. Now, let's determine if what I told you was a lie or not as a function of the truth of the antecedent and consequent. Well, suppose they're both true. The antecedent and consequent are true. So the class ends and the antecedent is true, right? You turned in all the homework. And the consequent is true. I gave you an A in the class. So the two inputs are true. In that situation, did I lie to you? No. When I told you the conditional, if you turn in all the homework, then I'll give you an A in the class. Clearly that I wasn't lying, okay? You couldn't, at the end of the class, come up to me and say, hey, you lied. You wouldn't have a good case to that effect. All right. What if, on the other hand, the antecedent was true, but the consequent was false? You turned in all the homework, but I didn't give you an A. Would you have a complaint to the effect that I lied to you? Well, yeah, 100%. Because I told you that if you turned in all the homework, I would give you an A in the class. You turned in all the homework, I didn't give you an A, right? That's as clear a case of lying as there is, right? So the conditional in that situation is false. Okay, so if the antecedent is true and the consequent is false, the conditional is false. What if, and this is the one that's a little tricky, but bear with me on this. What if the antecedent is false, but the consequent is true? You didn't turn in all the homework, but I gave you an A. So the antecedent was false. You did not turn in the homework. Consequent was true. I gave you an A in the class. Did I lie to you when I said, if you turn in all the homework, I'll give you an A? Well, no, I didn't lie. I may have left out some information. Maybe I just give everyone an A, right? So it's true that if you turn in all the homework, I'll give you an A. It's also true that if you don't turn in all the homework, I'll give you an A. Maybe it's also true that if you turn in half of the homework, I'll give you an A, because I just give everyone an A no matter what. But even if I give everyone an A no matter what, it's still true that if someone turns in all the homework, I will give them an A. So the conditional is still true in that situation. So I didn't lie. Maybe I left some information out that you might have thought would be important because you said, oh man, you could have told me, right? I spent all this time on all the homework. So you might have a gripe against me, but the gripe wouldn't be that the conditional was false. The gripe would be that there was more information I could have told you. Okay. Well, what if they're both false? What if the antecedent is false and the consequent is false? You don't turn in all the homework and I don't give you an A. Can you come back to me and accuse me of lying to you? Well, no, right? So really the only situation in which you really got a case that I definitely lied, where the conditional is false, is this one here. First input is true, antecedent is true, second input is false, consequent is false. In that condition, the conditional overall outputs false. The whole conditional is false. All of the other combinations, it's true. Okay. Next up is the biconditional. Okay. This is actually official UCSD policy for people who take a class, pass, not pass, PNP. So suppose here's two atomic statements. You earn a C- or better, and I'll give you a P, meaning pass in the class. And I tell you this biconditional. I'll give you a P if and only if you earn a C- or better. So it's a biconditional. Well, this one's pretty true. Pretty easy. Suppose both components are true. I gave you a pass and you earned a C- or better. Did I lie to you? No. Okay, so it's true. The biconditional is true if both of the components are true. What if the first is true and the second is false? I gave you a pass, but you didn't earn a C- or better. You actually got a D, right? Then did I lie when I told you what I would do, when I told you that biconditional? Yeah, because I told you I would give you a pass if and only if you got a C- or better. Well, you didn't get a C- or better, so that's a lie. What if the first is false and the second is true? I didn't give you a pass, but you did earn a C- or better. Well, then I also lied because I told you I would give you a pass if and only if you earned a C- or better. So I lied there. If they're both false, though, I didn't give you a pass. Okay, I gave you a not pass. And it's also false you earned a C- or better. You got a D, let's say. Well, then what I told you is true. The bicondition I told you was true. It was not a lie. Okay, so biconditional is actually pretty straightforward. Just think of it this way. A biconditional is true when both inputs have the same truth value. If they're both true, it's true. If they're both false, it outputs true. So if the two inputs are the same, it outputs true. When the two inputs are different, either first is true, second is false, first is false, second is true, but they're different, it outputs false. Okay? So those are the 5 truth functional operators. They're statement operators, but they also are truth functional operators. And that's it for now. Next up will be chapter 2.2 and 2.3.